Hello, this is Mr. Gilmore with the 4.4 Part 1 Parallel Application Proofs. Now that we've seen the use of our corresponding angles postulate to actually prove that we know that the lines will be parallel, and also the use of the corresponding angles consequence, actually showing then that we can find angle relationships based on parallel lines, we can actually then use these new tools that we have to reach into proofs using these new theorems. Let's take a look at what today's lesson is going to hold. So we have covered the tests. These are the ways that we actually can cut through lines and determine whether these lines have to be parallel. So if we were cut through lines with a transversal and we come across corresponding angles equal, or alternate interior, alternate exterior angles equal, or even consecutive interior angles are supplementary, then we can prove that the lines are parallel. The consequences are the lines that we find, or are the theorems that we find in which the lines are already given to us as parallel. And when we cut through with the transversal, then the result is knowing that some sort of angle relationship holds, which means when we cut through lines that are parallel, we'll find equal corresponding angles, we'll find equal alternate interior and alternate exterior angles, and we'll also find supplementary consecutive interior angles. Now we're going to use these theorems actually in a few proofs today. Let's take a look at our first example proof here. We are given in this diagram that we have actually two sets of parallel lines. AB and CD are given to us as parallel, and AC and BD are given to us as parallel. We're going to prove that angle 1 is actually equal to angle 4. Now, I have angles 1, 2, 3, and 4 labeled, but really I only need to know 3 of these angles. I'm only going to use angle 1, 2, and 4 in my proof. Let's take a look how I reach this conclusion. So step 1, state the given. So we know that AB is parallel to CD, and we know that AC is parallel to BD. So what can I then determine from that? Well, if I have sets of lines that are parallel, and I have other lines that are cutting through them, then I know I have some angle relationships. First, take a look at angles 1 and angle 2. Angle 1 and angle 2 are actually a consecutive pair of consecutive interior angles, which means I know what the relationship is based on the lines being parallel. So since the lines are parallel, I know the consequences, which are this. I know that angle 1 and angle 2 are supplementary. So which theorem did I then use to then determine that conclusion? I use the consecutive interior angle consequence. It's a consequence of knowing the lines are parallel. Well, what can I then follow up with that? Well, I could say something then about angle 2 and angle 4. As it turns out, angle 2 and angle 4 are also supplementary by the same reason. I know that they're also consecutive interior angles and their lines are parallel, which means they have to be supplementary as well, using the same reason, CIAC. So then what can I then conclude about angle 1 and angle 4? We'll take a look at our statements in statement 2. Angle 1 is supplementary to angle 2, and angle 2 is also supplementary to angle 4, which means I know something about angle 1 and angle 4. They have to be equal by the same supplements theorem. Angle 1 and angle 4 are supplementary to the same third angle. And so there we have it, our first example proof of using one of our consequences to actually prove a result about our angle relationships. Let's take a look at another example. In this diagram, we actually have what's called a trapezoid, which we haven't talked about trapezoids yet, but a trapezoid is a quadrilateral with precisely one pair of parallel lines. We're given that AB and CD are parallel. We also have A connected to C, B connected to D, and we have this point of intersection at point M. We're going to prove that the measure of angle MDC and the measure of angle MCD are actually equal to each other. That happens to be these two angles right here. We're going to prove that those two angles are going to be equal to each other. So where do we begin? Well, the first thing I would realize is I am dealing with parallel lines, which means whenever I cut those parallel lines, I will actually have angle relationships. As it turns out, I am cutting those parallel lines. That's what BD is doing. That's a transversal. It's cutting through those parallel lines, and that's also what CA is doing. That's a transversal as well. So I'm going to be using those transversals here in just a second to determine some angle relationships. So let's start with our given. AB is parallel to CD, and AM is equal to BM, given. So what do I know first? Well, I already have something at the very top of my diagram I'm going to work with. If I take a look at AM is equal to BM, I know that these two angles here, the measure of angle MAB and the measure of angle MBA, have to be equal to each other. So the measure of angle MAB is equal to the measure of angle MBA. MBA. And the reason why is because I'm dealing with an isosceles triangle there, which means by the ITT, I have a pair of equal base angles. So where am I going to use that then? Well, there's a relationship with those pair of equal base angles with the pair of angles that I want to prove equal. Take a look at angle MAB, this angle right up here, and the angle MCD. Notice anything special about them? If AB and DC are parallel and that's a transversal AC, that means that angle MAB, this one right here, and angle MCD, this angle right here, they are a pair of alternate interior angles, which means I can claim the measure of angle MAB is equal to the measure of angle MCD by the alternate interior angle consequence. I'm cutting a set of parallel lines, which means by the consequence I know that alternate interior angles are equal. At the same time, MBA and MDC also are a pair of alternate interior angles. So I can claim that those two angles are equal as well. So our last step then is a really big happy family of transitivity of equality. Let's take a look at why. I can go ahead and claim that triangle that the angle MDC is equal to angle MCD, and here's why. Take a look. Angle MCD is equal to angle MAB, and angle MAB is equal to angle MBA, and angle MBA is equal to MDC, which means the measure of angle MDC is equal to the measure of angle MCD. And there we have it. All four of these angles happen to be equal to each other. Pretty cool, okay? And that's, again, using our parallel consequences. Let's do one more example here then. Take a look at these two triangles here, ABC and CDE. We're given that in each of these, that they have a pair of equal angles. We're given that angle 1 is equal to angle 2, and that angle 3 is equal to angle 4. We're actually going to prove, in this case, a set of parallel lines. We're given a set of parallel lines already, that AB and CD are parallel, but we're also going to prove that we're going to prove that BC and DE are parallel. We don't know that they're parallel. I should not mark those on the diagram. So let's then take a look at how we're going to tackle this proof. Let's start off with our given. So we know we have measure angle 1 equals measure angle 2, and we're given the measure of angle 3 equals measure of angle 4, and we know we have a set of parallel lines. Well, because we have a set of parallel lines, that's where I'm going to begin. I have sets of parallel lines, which means if I cut them with transversals, I know their angle relationships. We'll take a look at AB and CD. They are being cut. Look at that. Look at this line right here. That line is cutting right through them, which means I have a pair of angle relationships going on. Take a look at what I'm going to find. Take a look at angle 1 and angle 3. Notice something special about them? Those are corresponding angles. And because they're corresponding angles and we've cut them with a set of parallel lines, then we know that those corresponding angles are equal. So the measure of angle 1 is equal to the measure of angle 3, and that means we have another pair of equal angles there by corresponding angles consequence. And moreover from that, take a look what happens. If 1's equal to angle 3, and 2's equal to angle 1, and 3's equal to angle 4, that means by a very big happy family transitivity, we also know the measure of angle 2 is equal to the measure of angle 4, and that is by transitivity of equality. So take a look. We now know that angle 2 and angle 4 are equal. Now, why is it important then that we know that angle 2 and angle 4 are equal? Here's why we know. Or here's why we want that. Because take a look at their relationship. These lines I want to prove to be parallel. Well, angle 2 and angle 4 are now an equal pair of corresponding angles. So I can claim the lines to be parallel, BC and DE, because of the corresponding angles postulate, that if we have a pair of equal corresponding angles, then the lines have to be parallel. And that's where we end up with the two lines BC being parallel to DE because of actually the corresponding angles postulate. So we actually, it's a neat proof. Take a look. We actually use two reasons. We use a consequence to prove something about an angle relationship, and then we use an angle relationship to prove that we have a set of parallel lines. Very neat proof. So we come to the end of this lesson. What you'll see on your homework assignment is something similar, where you'll work through example after example of using either your corresponding angle or using your consequences to prove something about angle relationships, or using your test to prove something about parallel lines. If you do have any questions on that homework, please be sure to email me about that. With that, be good and do good.